Day 337, Applied Business Statistics, and we are going to get started, as we often do, with a COVID-19 update where I get to talk about statistical graphing and then go off on rants about things like choices that people are making with the use of their statistical graphing. So, the New York Times has been keeping track of how many cases are occurring at colleges all over the nation. And if you haven't seen this particular list, it's well worth checking out. I wanted to drill down a little bit on Missouri and see what's happening in our region. And so I pulled some of them that are close to us. We have College of the Ozarks, Drury University, Evangel, Missouri State, and of course University of Missouri, or Mizzou in Columbia. And here's what the numbers look like. Now, the ones that I want to point out to you would be Drury, and of course us, and then I want to talk about College of the Ozarks with their 2 cases. So first of all, both Drury and Missouri State are in Springfield. Drury has 60 cases and Missouri State has 924. Now, part of the reason for that might just be the number of students. So we should look at what is our denominator. That is what helps us make decisions about comparisons for numbers. You can't just compare the raw numbers. And since I don't have those numbers, we're just going to have to give the fact that Drury is a smaller school than Missouri State, so they're going to have fewer students. So that explains part of the reason why their numbers look like they do. But they also do something else. And that is a regular routine of testing. So for instance, students are tested on Tuesdays, employees are tested on Fridays. And to date, they've had roughly 360 students and 137 employees tested. So what you would have as a student is kind of a randomized lottery in which you might get an email and they say, hey, you've been chosen, come on in and get a test. And of course, if you have symptoms or you're worried about having contracted COVID, you could certainly go get a test as well. But they're doing a different testing regimen. And this might be one of the reasons, or it certainly has been one of the reasons that have been identified as what makes the difference in keeping numbers low versus high. So we have a randomized testing regimen as opposed to testing only when you have any symptoms. This is how Drury is displaying their numbers. Part of this I really like. I like this table because it's broken out by students, faculty, staff, and you get the totals. On campus, off campus, the Drury Go campuses, and then we get the totals for those. So we're getting, we're called marginal totals. Marginal meaning if we go all the way to the right under total, that's a margin, and that's the total for each row, and we're also getting totals for each column. This makes it really easy to compare because we can take the total cumulative cases, either current cases at 24 or a total cumulative at 93. Remember, their number, according to the New York Times, was 60. So that number should be updated to 93. This is what's called a lagging indicator. Lagging indicators are those that fall behind time. And so when something happens, it takes a while for that to be reported. This is what we're seeing with New York Times is definitely a lagging indicator. We're seeing that a little later than what we get with this. Number of deaths compared to number of cases. Number of deaths is a lagging indicator because people can contract the virus, many of them recover, but you've got to wait 6, 8, 12 weeks, you've got to wait a certain amount of time before those numbers of those who will pass away show up in that lagging indicator. The opposite would be a leading indicator. That's when something happens and you say, uh-oh, here's what we predict for the future. This indicator, often financial indicators, when you see certain trends, you say, oh, this looks like we're leading toward a recession or a boom market, or we're able to make predictions with a leading indicator. So what I like about the table is that it gives us lots of information in a fairly compact version that we can then make comparisons. But then they do what is essentially a pie chart. I suppose we could call it a donut chart. It looks like a pie chart with a hole in the middle. And this gives us some gray circles, and we're supposed to learn something from that. Here's what's wrong with this. So this I dislike terribly. This is done very poorly. Number one, if you look at the gray circles, these are number of negative tests versus number of positive tests. For students, 203. For staff, 47. For faculty, 20. but look at the size of the circles. If they wanted to at least do this a little bit better, they could adjust the size of those circles to be relative to the size of the number of cases. But we have the same number of, let's say the same amount of real estate in those circles, and it doesn't matter whether it's 20 cases or 200 cases, the circle is exactly the same size. So that makes it non-comparable across groups. So that could be fixed, but pie charts and donut charts are really not great ways to display data. The other problem with this is they have positive tests for staff and faculty are both at 0, which just means you have a gray circle. It's just one data point. So this doesn't help. What these numbers should display would be the positivity rate, which should be presented as a percentage. So what we should have is number of positive tests for students that would be 10 out of total number of tests, which would be 203 plus those 10, roughly 5%, just under 5% positivity rate. Now that number can tell you something because that can be compared across groups. So we should have roughly 5% compared to 0% and 0%. Now we can learn something from this. So some things that I like, some things that I don't like about the way these data are being displayed. Now the other school that stood out to me was College of the Ozarks, which has 2 cases and has had 2 cases for the last 4 or 5 weeks, at least as long as I've been following this particular website. Now when I see 2 cases and I see this consistent over time, it makes my statistician brain get a little suspicious. What's going on with these numbers? Why are they not changing as we would expect? So I went to their website, and here's what I found. I started with Taney County Health Department. So what is going on in the surrounding area? Does that number 2 cases, match up with what we see in what's happening in the rest of the county? Now these are numbers from the health department. So these are the scientists. So public health scientists are telling us that there are 800 confirmed positive cases in the county. Well, why are there only 2 then at the college? As I dug a little further, I found this. It says, if an employee or student were to test positive for COVID-19, if in the unlikely case this were to happen, the college will update COVID-19 dashboard on Campus Web. So what's that? Well, the Campus Web is this link here in the upper left. This is just a picture of the website, so there's nothing to click on. But I did click on it, and this is like a paywall, essentially. So you have to have a login to be able to get to Campus Web. So what that means is these data are not on the free web. They are hidden behind we'll call it a paywall, something you have to log into. And so we're not getting those numbers. So why is it at 2? Don't know for sure, but it's not easy for, let's say, the New York Times to go out and scrape this website and get those numbers. So I guess Hard Work U is working hard at hiding the data, which is not exactly what you want. I also found that they said that COVID-19 is a special strain of coronavirus, family of viruses that includes the common cold. Any problems with that? So coronavirus, I found out, actually can cause common cold, but the most common cause of common cold is a rhinovirus. And so I dug a little deeper to find out what is the difference. So coronavirus, if you've seen the images of the virus, you see those little stalks sticking out of the virus? That's what makes it a coronavirus. It's like a crown of these little thorns sticking out of the virus. Okay. And if you look at a picture of a rhinovirus, it's smoother. And so it doesn't have that, I guess, RNA or DNA or whatever's causing those spikes. Rhinoviruses don't make you seriously sick, but coronaviruses, those are the ones that are part of that family that can make you very, very sick. So for instance, coronavirus would probably be better to be described instead of common cold. This also includes SARS and MERS and all the really heavy-duty viruses that could really mess you up. So you could look at this and say, are they minimizing this? Is there a reason why they're displaying it that way? Well, that's what I learned from looking at this website. And of course, we got to look at MSU, see where we stand. The bar charts We're down to 4 weeks now, so we still don't have that baseline from where we began. So I added that for them, fixed it for you. And then we can see where we are in these relative numbers. These are, of course, 7-day totals. So we get to see the relative flow of these numbers as they're changing. These numbers are going down, which would seem to be a good thing. This is also from New York Times. These are the places of all 50 states, which states have the greatest number of cases. So where are the hot spots? Looks like North Dakota is number 1. Remember, for the longest time, North Dakota had almost no cases. Now, all of a sudden, it's becoming a hotspot. South Dakota, Arkansas, and Missouri. So now we're part of this growing trend. You can see that trend over time. So here's what I want to point out. 24 cases per day per 100,000. Like, how many students do we have on campus, do you think?
I think I read 13,000.
13,000?
I believe.
Okay. So let me kind of play a little loose with that math. Let's say it's 10,000. Okay, just make the numbers a little easier to understand. So we have 104 over the last 7 days, so 14.8. We'll round up to 15. So 15 cases per day per 10,000. Well, if you have 24 cases per 100,000, that we just change that by an order of 10, that'd be 2.4 cases per 10,000. So we're comparing roughly 2.4 to 15 per day, Missouri State compared to the state of Missouri. And if we go back a week, 267, 7 days, that would be what, 38-ish. So we're comparing numbers of 2.4 and 3 per 10,000 to numbers like 15, 38, 383 divided by 7, 54, 55, rounded up to 55. So we're dealing with numbers much higher than we would see or we would expect to see in the general public. So now, I want to talk to you about the unit test number 1. Let me start with this. I used a data set as an example data set, and so what I did was I took the data set that I intended to use for the test, and I changed it up a little bit, and I used that as an example in one of the videos, thinking that I'm going to use the other data set for the test, and I'll use this example data set for the example. Well, foolishly, I know this is basic data, I didn't change the name of the data set, as I should have. And so that means that when I was rushing to get everything put together for the test, I posted the wrong data set, which means that if you started the test using the data set that I did post, you got all of those answers wrong. So I posted the correct data set, or at least the data set that corresponds to the answers that are already coded into test number 1, and I called that fixed. It has the name of the data set plus fixed attached to that. That's the one you should use. So don't use and I've already taken down the original, the wrong one, right? And the only one that's available is the one that says fixed. If you have already done the test and you got those all wrong, just send me an email. I can clear that for you and let you redo it. Because it's no fair to make you take a test over the wrong data set. Do you have any questions about test 1? Anything you'd like to know? Anything to make it easier, more helpful?
Just one time for each of them.
Okay, so do you remember in the independent samples t-test video where I started with the Excel spreadsheet and then I took those numbers and I put all the scale values into one column, okay, and then I created a second column. I think it was load and no load would be the values for that particular mutual fund data set. That's what you need to do first. And of course, save that as a CSV.
That's my other question, is we do need to edit this data before we're running it in JAX.
Correct.
Okay.
Correct.
And that's
a very common thing. You need to
independent sample
restructure.
t-tests?
I say again?
That's just independent sample t-tests that you're going to need to change the data for?
Well, for this class, yes. In the real world, restructuring data is a very common part of running an analysis. So that's why I'm introducing that now. You should not assume that whatever data set you get out in the wild is going to be structured in the way that you need it to be. So it's important that, from the very outset you're thinking, what do we need to do with these numbers to run the test that we need to do properly with them.
Okay.
Yep. Any other questions about the test itself? Okay. So let me just quickly review. So we have the test coming up on, well, you can do it anytime between now and Sunday night. I'd encourage you to do it like, Friday or Saturday at the latest. And certainly don't wait till midnight on Sunday for, because I won't be awake. So if you have any questions, the way you should approach it is get those two data sets, run those. You'll first of all need to open them in Excel. You need to restructure one of them. You'll run the independent and the paired sample t-test, and then you'll use the answer sheet to write, here are the answers, here are the findings. And keep that with you. And when you've studied the study guide, you know the answers to everything on that study guide, then it's time to go to Blackboard and click on the link and start that test. You have 90 minutes to do, it's essentially 50 questions, but a big chunk of those are things you've already done in JASP and you're just writing out the findings. So you've got 90 minutes to do like 25 questions, plenty of time. So you click on the link, you start the test, you'll answer some true, false, and some multiple choice questions, and then you'll enter the findings from your JASP tests. And those findings, it's the same structure as what we did in the previous 2 weeks. So, and am I right about that? We were talking about that earlier, that, they follow exactly what we've done previously. So you're being tested over things we have already done. Enter that information, and you're good to go. Have any questions for me?
I haven't looked at the material for this week. Is there also a regular weekly assignment, or is it just a test?
Thank you for mentioning that. There is a regular weekly assignment, but you'll notice it's more, there's not as much there. There's just 2 sections. There's very little, so it gives you more time to study for the test.
Okay.
So yes, there is a regular weekly assignment, but it's not as heavy or complex. And then we'll get into ANOVAs and chi-square in the next 2 weeks, 3 weeks.
So if you could explain a scenario behind it, that'd be great.
Well, I am so glad that you asked, because that's what I'm going to talk about now.
Okay. Cool.
So that wasn't a setup. You actually just asked that question out of the blue. But it is a perfect segue into what I plan to talk about, which is the null hypothesis, the alternative hypothesis, how we structure them, how we interpret them. And so I'm going to use this example called babies and hypothesis testing, because, who didn't like babies? The question is, how much does an average baby weigh? I would be curious. Give me some numbers. Like, what do you think a baby weighs? What do you think?
8 pounds.
8 pounds? Okay, good. What do you think?
9 pounds.
You guys are actually getting pretty close. And any other guesses you guys want to offer?
Yeah, I was going to say 8 or 9 pounds.
8 or 9? Okay, very good. Now, what is the range? Sometimes people say, I had a baby, weighed this much, and they give you a low number, and you think, wow, that baby was premature. Or they give you another number, and other people will say, oh, wow, that was a big baby. So what would be a low number? Normal, but low.
6.
So we'll go 6. Any other guesses?
4.
4. Okay. I think 4 would be especially low, but I don't know, we'll find out. Now what would be big? What would be like a high number?
13?
13? 13 would be big. You're absolutely right.
13 pounds.
So underweight, anywhere from 4 to 6, and large, certainly 13 would qualify for that. So here are the values that I found with a quick little internet search. In developed countries, the average newborn weighs 7.5 pounds, or 3.4 kilograms, with a range of 6 to 10.1. So that is the point estimate, 7.5, and the range in which we would call normal. So what we've established is some boundaries and an average, and we can do some comparisons. So if someone says they had an 8-pound baby, you're like, oh yeah, that sounds about right. And if they have a 13-pound baby, that would be heavy. So now you have some numbers that you could keep in mind that you could use to make comparisons. So you're reading on the internet, you find a story about a Siberian woman who gave birth to a 17-pound, 1-ounce baby. True story. I know because I read it on the internet. It's a real story. Actually, it came from Reuters, so it is real. But let's say you read this story and you get curious, like what is going on with Siberia? And so you decide to do a little research, and here's what you find. That 17 pounds, even in Siberia, is pretty big. But in Siberia, women routinely give birth to babies that average, so we take all of the weights, add them up, divide by number of babies, average is 11 pounds. And what you want to ask is that 11 pounds statistically significantly different than the rest of the world? So we go back to what we've learned from our overall averages. For instance, in developed countries, the average baby weight is 7.5 pounds. And we looked at the range. So is 11 extreme, or is that kind of within the range that we would consider normal? That is the question that we're asking when we do hypothesis testing. We know large numbers, averages, in this case it would be the population, and then we can take a sample. So we have a Siberian sample compared to the world population. And we're going to do a test to figure out if our sample is different than our population or if it's kind of in the realm of what is expected from our population. Does my Siberian sample mean represent the world population mean? Now it is different, we can just tell that from looking. But is it statistically significantly different? Is the difference that we find due to chance or error, this is randomness, or is there some kind of an effect in Siberia? We are not at this point trying to explain what that effect is. We're not saying it's the water or it's the radiation or the fallout from Chernobyl or something. We're just saying it's different, it's really different. And then that might cause us to go do deeper exploration and find out what might be the true cause. Right now we're just working in statistics. So is there a statistical difference that we might want to follow up on? So our two options are, yes, babies just happen to be a little larger in this part of the world for reasons, it's just randomness. That's chance. Or, no, there's something really going on here that explains why babies are so much heavier on average than in the rest of the world. The hypothesis that we test is the null hypothesis, which says that there is no difference. So we say that Siberia is part of the world population. So that 7.5 also includes the Siberian mean. It obviously is not exerting a lot of leverage on that mean, but it's included. It's part of the population. So we're going to start with the idea that Siberia is part of the world population. Their numbers get combined with everyone else's numbers, and so really they're just on the high end of the scale. That any differences that we observe are due to chance. That is the null hypothesis. That is the hypothesis that we're going to test. But we also want to posit an alternative to that, an alternative hypothesis, which says, well, maybe there really is something different. Even though this sample was drawn from a population that has a mean of 7.5, this sample is truly different. And we're going to use some statistics to figure that out. So this is how we think through our null and alternative hypothesis. Null hypothesis says that there is no difference. Now here is what it would look like if we just express that in words. The average weight of babies born in Siberia will be no different than the world average of 7.5 pounds. So when I say the hypothesis posits that there is no difference, we would write it just like that. We'd say there is no difference. That would be part of our hypothesis. Sometime in the future, if you're working on a thesis or a dissertation, and you will need to articulate the null and alternative hypothesis as part of that process, this is how you should write it. Express the groups that you're comparing and the value that you're expecting, and no different. You actually put that into the hypothesis. Here's what it looks like in numbers. H sub 0 mu equals 7.5. So how would I read that? I'm saying that my null hypothesis, my H sub 0, is that the Siberian sample mean is drawn from a population that has an average of 7.5. Mu equals 7.5. I'm saying the sample comes from a population with an average of 7.5. Remember, mu is the mean of a population, whereas x bar, or m, will be the mean of a sample. The other way that I could write this is mu1 equals mu2. And we've done this with the before and after, the paired samples t-tests, where we have we have one group being measured 2 times, and we're comparing their first measurement from their second. We're saying that they are both drawn from a population that has a mean equal to the other. So I could write it in either of these 2 ways. The alternative hypothesis would be that one group is going to be statistically significantly different than the other. And in words, we would say this: the average weight of babies born in Siberia will be different than the world average of 7.5 pounds. And if you compare that to the null hypothesis, you will see that the only difference between those 2 is no different, and the alternative will be different. Everything else about that sentence is exactly the same. So how would we express the alternative hypothesis in numbers? Notice how similar this is to the null. H sub 1 colon mu does not equal 7.5. So the only difference between the alternative and the null, in the null we have an equal sign, in the alternative a does not equal sign. It's the equal sign with a slash through it. Going back to terminology, you will always see the null hypothesis written as H sub 0 colon. That's always consistent. The alternative hypothesis may be written as H sub 1 colon, H sub A colon. I've seen it as H sub alt, ALT, for alternative hypothesis. I like to use H sub 1, H sub 2, H sub 3. I think it gives you more flexibility in explaining the alternatives. But you can do it in other ways. H sub A was another common way you might see this written. So alternative hypotheses may have a direction or not. A directional alternative hypothesis is where we say that the sample mean will be higher than or will be lower than the population mean. So in this case, I might write H sub 1, mu is greater than 7.5, or a higher than hypothesis. But this is also called a one-tail test. We're interested only in one tail of the distribution, either the left end or the right end of the distribution. So why would we do that? So if we think about a manufacturing process where we have plastic jugs that we're filling with detergent, and you know from buying, well, pretty much anything, you can look at the label and it says this contains 32 ounces. Does it always contain exactly 32 ounces? 32.0000 all straight? Well, of course not. No, it's going to be 32.01. So there will be some variability. Some will be slightly more than 32, slightly less than 32, but we have a range in which this filling of the jugs may occur. Now, are people going to get angry and write you nasty letters or talk about you on Facebook if they expected 32 ounces and you gave them 32.5 ounces? So if we're over that amount, nobody cares. That's not a problem. But if you have 31.9 ounces, somebody somewhere is going to be upset that they didn't get that 1/10 of an ounce. So the undervalue, that's what matters. So what we would do is we would set a fence, like critical value, like we talked about last week. We're only interested in low values. Is the filling of these containers less than an established value? So do you see how the far end of this, the positive end of the scale doesn't matter. It's only if we're too low. That's why we would use a one-tailed test. Or we have a certain drug that's designed to, I don't know, improve something, make something better. It's supposed to change to the positive end of the scale. If there is no difference, nothing changes from taking the drug, or if it makes the problem worse, both of those are bad outcomes. We're not going to market that drug. So the only change that we're really interested in is to the positive direction. A one-tailed test is where we're only interested in change in one direction. So one tail, one direction. To remember that, you can think about this cute little picture. A one-tailed test, you have just one tail, you can only go in one direction at a time. The alternative to this would be a two-tailed test or a non-directional test, where we're looking in both ends of the curve. This is the most common structure. Non-directional test, we're saying that the mean of the sample will be different than the mean of the population, but we're not saying whether it'll be higher or lower. It's just different. Now, you'll note in some of the examples that we've done, I've structured the question like, is one of these groups greater than the other group? Does one of these mutual funds have a better outcome than the other? Do you see how that's still a two-tailed test? If I say, is one going to be better than the other? Have I really established a direction? No. Because I'm not saying which one will be better. Now, if I said, will the no-load funds have a better return than the load mutual funds? That establishes a direction. Because I'm saying this one will change in this direction relative to the other one. So a two-tailed test is just simply mu does not equal whatever the value, in this case 7.5, whatever that mean of the population value is from our null hypothesis. So how do you remember the two-tailed could go in two different directions? Well, if you have two tails, you go in two different directions, which is just not the cutest thing you ever saw. Right, so remember, two-tailed test, just think of the two dogs kind of curled up together, tails going in very different directions. So let's go back to our setup. We talked about baby weight. How would we actually structure this for our example? We would start with a null hypothesis, where we say mu equals 7.5. We are saying that the Siberian sample mean has been drawn from a population that has a mean of 7.5, and our mean for our sample of babies born in Siberia will be no different than the world average of 7.5 pounds. No difference. The alternative, H sub 1, mu does not equal 7.5. We're saying that the average weight of babies born in Siberia will be different than the world average of 7.5. The hypothesis that we test is the null hypothesis, the one that says there's no difference. We will reject the null hypothesis if let's say the t-test is statistically significant. We will fail to reject the null hypothesis because we never actually accept the null hypothesis. So we would fail to reject the null hypothesis if the test was not statistically significant. And do you remember the three ways that I showed you on how to interpret that test? Is the t-value greater than a cutoff score? Is the p-value less than 0.05? Does the confidence interval cross 0?
If the p-value is less than 0.05, that means it is or is not significant.
So let me review that. Okay, so if the test is statistically significant, here's what will happen. The t-value will be greater than the critical value. So t greater than CV. Again, this is if it is statistically significant. The p-value will be less than 0.05 if it is statistically significant. And the confidence interval will not cross 0. It will not include the hypothesized value of 0. If the test is not statistically significant, then we'll see the opposite findings. So the t-value would be less than the critical value. The p-value, your probability, would be greater than 0.05, and the confidence interval would cross 0. One of the values will be negative, one will be positive, crossing over the 0 mark, if it is not statistically significant. So now what I'd like to do is just do some quick practice. Null and alternative, directional, non-directional. Just to reiterate this, the null hypothesis is always the same structure. In other words, it's always the no different or the same. Alternative hypotheses can be directional or non-directional. So there is no directional null or non-directional null. It's just the null hypothesis. There can be a directional or a non-directional alternative hypothesis. So I'm going to work through each of these with you. And what you should first ask yourself is this null or alternative? And if it is alternative, is it directional or non-directional? So let's start with this one. Test scores will be higher at State U than at other colleges. Is that null or alternative? So an alternative, is it directional or non-directional? It is directional. So we're saying the scores at this school will be higher than that school. Alternative, directional. There will be no difference between the scores of the deaf rats and the hearing rats.
No.
That is a null hypothesis, because we're saying no difference. Blind people have better hearing than sighted people. It's an alternative, and it is directional, because we're saying this group will be higher than, better than the other group. Okay, now watch this one. Drinking caffeine may lead to higher test scores because it increases alertness, or it may lead to lower test scores because of the jittery side effects. So first of all, null or alternative? Alternative. Is this directional or non-directional?
Non-directional.
Very good. Non-directional, because we're saying it could go this way or it could go that way. And if we're not establishing a direction, there is no difference in the test scores between the group listening to Frank Sinatra and the group listening to Marilyn Manson.
No.
That is a null hypothesis. So let's practice this in a slightly different way. Writing your own hypothesis. Null and alternative. So here is the research question. Is the amount of sugar in children's cereal different for Cheerios and Frosted Flakes? As a null hypothesis, you would say something about no difference, and you put it in the context of the two groups, in this case Cheerios and Frosted Flakes. Would anyone care to talk out and hazard a guess of a way of structuring this as a null hypothesis? Sir?
There is no difference in the amount of sugar between Cheerios and Frosted Flakes.
Nailed it. There's no difference in the amount of sugar in Cheerios and Frosted Flakes. That's exactly what I had on my notes. Wonderful. How about a non-directional alternative hypothesis? Anybody?
There's a different amount of sugar in Cheerios than Frosted Flakes.
There you go. It's different. We're not saying which one is higher or lower, just that it's different. Excellent. Let's do one more. Does eating salty food make your blood pressure go up? Okay, so there's actually two groups here. What are the two groups? High blood pressure versus regular blood pressure. That's what's implied with that. Okay? So we could structure this. Well, anybody want to take a guess at a null hypothesis about blood pressure and salt?
Salty foods have no effect on blood pressure.
Perfect. So salty foods has no effect on blood pressure. There's no difference in your blood pressure based on eating salty foods. And how would we make that a directional alternative hypothesis?
Eating salty foods will make your blood pressure high.
There you go. Eating salty foods will increase your blood pressure. That's how it works. We're testing the null hypothesis. We're looking for evidence. And we're making a conclusion about the null. So we start with the idea that there's no difference. And you remember the reason why we start with that as our hypothesis the one that we test, is because we know, in fact, that there will always be differences. That this jug of detergent will have slightly more or slightly less than the next one. And that this baby will weigh slightly more or slightly less than others. We know that there are always going to be variations. But there's a variation in which we say, it doesn't matter. That's just randomness. So if you get 32.1 ounces, I got what I paid for. And even 31.9, you're getting what you paid for. That's not enough of a variation to be bothersome. But then there's a range outside of which we say, wait, that's too much of a difference. If you were to pick up a jug and it just felt half empty, wait, this can't be right. So we have our starting point of no difference, knowing that there's always going to be differences, but they're really not differences that matter. And then we're setting a fence, a cutoff value, in which we're saying values outside of this are just too different to ignore. These are values that are too extreme for us to say these differences are due to chance. So that's how we do our hypothesis testing. Thank you so much for being here. I'll see you guys next week.